We talked about solving with one-to-one properties, but in each of these problems, I did not talk about step 4. With logarithms, you should be checking for extraneous solutions. So what is an extraneous solution? That's what we're going to talk about in this video. Extraneous, I got this from Wiktionary, is not belonging to or dependent upon a thing, without or beyond a thing foreign. So you see extra as part of the word. It's one of the roots. It means extra, but specifically something that's extra that doesn't belong. And in math, we talk about something being extraneous if it's a number at the end of a solution process that does not make the equation true. So occasionally we can do things that give us extra solutions. One straightforward example is if we took the equation, say, x equals 2 and squared it, we get x squared equal 4. We would never do this just for fun, but when you solve this, you get two solutions, x minus 2, x plus 2 equals 0. So we actually get the solution 2, but we also get the solution negative 2. It's not actually a solution to the original problem. It came about when we squared both sides. So negative 2 did not make the original equation true. So this happens a lot when we are dealing with logarithmic equations. We need to check for extra solutions that don't actually make the equation true. So I'm going to give you some that have extraneous solutions and some that don't. Here we can use the one-to-one property since they have the same base. Negative 50 plus n squared equals 2n squared plus 15n. This is quadratic, so we should get everything on the same side. Zero equals n squared plus 15n minus 50. Sorry, plus 50. That's supposed to be a plus, not minus 150. So n plus 5, n plus 10. Our solutions are negative 5 and negative 10. Let's check them. That's the process that we need to do. So if we take negative 5, square it, that'll be positive 25. And then we add negative 50. So that would be negative 25. Can we take negative 25 and plug it into natural log? No. Therefore, this was not a solution. That doesn't mean that negative 10 is a solution, but we should check it. So negative 50 plus n squared. So that would be negative 50 plus 100 because we square it and we get a positive version. So we get 50. So it worked on that side. Let's double check on the other side. Yeah, this would be 200 and negative 150 when we substitute in 10. So that becomes a positive 50. Yes, this is a solution. So really, there's only one solution. Even though we got a quadratic, the quadratic had two solutions. Only one of them is actually a solution. So negative 10 is the actual solution, and negative 5 is an extraneous solution. It is not actually a solution to the original equation. Here, using our product rule, we can simplify the left side. So log base 8 of x minus 3, x minus 5. Then we can use our one-to-one property to say that this is x squared minus 8x plus 15 equals that whole input to the right side. Get everything on the same side. So we have x squared minus 28x plus 132 equals 0. We have x minus 6, x minus 22. So 6 and 22 are our potential solutions. Let's substitute those in. 6 minus 3, that works. 6 minus 5, that works. Now I'm just checking to make sure that they can be substituted into log. 20 times 6 would be 120, minus 117 is 3, so that's fine. 6 is an actual solution. Let's try 22. 22 minus 3 is 19. We can substitute that in. 22 minus 5, that's fine. 20 times 22, that's pretty big, and when we subtract 117, this will also work. So actually, this was an example where both of them are solutions. You don't always have extraneous solutions with a logarithmic equation. There are two solutions to this equation. They are 6 and 22. That's fine. But you should check them to make sure that when you put them in, the whole input ends up being positive. These log base 10s combine to x squared plus 3x. Now this we don't actually solve with the one-to-one property. Here we can use our inverse property. So this is 10 to the first, or 10. Move everything to the left side, so x squared plus 3x minus 10 equals 0. X plus 5 times x minus 2 equals 0. So we have negative 5 and positive 2 are our potential roots. Negative 5, can we substitute that in? No, we can only substitute in positive numbers. 2, log of 2, that works. Log of 2 plus 3, that works. And yeah, so x equals 2 is our only solution. Usually we just write it as x equals 2. We don't even bother saying the negative 5. But occasionally I might ask you, what is the extraneous solution that arises? Last one. Same log, so we can say x squared minus 1 equals negative 5x minus 1. Get everything on the same side. X squared plus 5x equals 0. So x times x plus 5 equals 0. So x equals 0 or negative 5. We plug in 0, we get 0 minus 1. That does not work because then we are substituting in a negative. So 0 did not work. Let's try negative 5. Negative 5 squared would be 25 minus 1. That's fine. This would be 25 minus 1. That's fine as well. So actually, it's very common that people will think, oh, it's a negative number, so it can't actually be the solution. No, it can, as long as when you substitute it in, the entire input is positive. So this whole thing ends up being positive 24, so it's fine. This whole thing ends up being positive 24, that's fine. So the whole input has to be positive. That doesn't mean that your solution has to be positive. And in fact, there are times when positive numbers are extraneous solutions and negative numbers are actual solutions. That's how you figure out whether a solution is extraneous or not.